Again, I've said to a bunch of you that I am giving you till Sunday at midnight to finish off any of these things that we've had in the last week. It's been kind of a quick week, but we've got an Ohm's Law lab. That's the one where you have to make the graphs. We've got the loads in parallel and series. That's where we use the online, the virtual circuit. You've got a sheet that was on current and amps. That's the loop rule and the junction rule. And then the sheet that was the circuit analysis that put everything together, okay? Many of you are already done all of those. That's excellent. But many of you aren't. And so please, let's get that in. Again, the demonstration of learning has the requirement of having things completed on time. Okay, now, yes, we're finishing off today. This is not a very long note. It's going to be an application of one of the equations that we already know. So we're kind of taking what we know and we are going to be using it to do some calculations. There is a practice sheet. You will notice also that I have posted the review for Monday already, which has some textbook questions, but I've also created, you can even think of it like a little practice calculation part of the test, where I've given you another group of questions that deal with our equations, and I've also put the solutions on there as well, so you can check your answers once you're doing them. Yep?
So are we reviewing on Monday?
You're reviewing on Monday, but I posted the review work so that if some of you wanted to get a start on the review over the weekend, then you would be able to have questions for me on Monday if you wanted to get a head start on that. Okay, the test is on Tuesday. Okay, so cost of electricity. All right, before I advance the slide and we talk about it, and I see some people are already writing ahead, so they don't get to answer because they're going to know the answer to this question. But when your parents pay the electricity bill, don't say electricity to the answer of this, but what are they paying for? Now, we have many properties of electricity that we've learned about. We've learned about current, we've learned about volts, we've learned about resistance, we've learned about power, and we know that there are two versions of power, IV. We've learned about many properties of electricity. So when they pay the electricity bill, what are they paying for? Yep. That's nice. That's good. You're right. They got to get it there. But which of our properties of electricity are they buying? They're buying something. Which are they buying? What do you think? They're buying current. So they're somehow the current's being measured, and whether you use more or less current, you're paying for current. I like that answer, but that's not correct. That's not correct. But that's a good idea. You'd think the more current you use, the more you should pay. All right, but that's not correct. Yeah, what do you think? So you're paying for volts. How many volts are in a standard home circuit? Yep, 120. Does it change? No, it changes a little bit, right? I said it fluctuates a little bit. If you're paying for just volts, then you would be paying the same bill every month because it's always 120. Do you see what I'm saying? Did you see the logic there? Because it's always 120, but so it doesn't change. So you'd have the same bill every time. So it can't possibly be volts. You see the logic? Excellent. This is what I want to go through. I want us to figure out what we're buying. So that was a good answer. Not quite current. Currents and volts. We're getting closer. What do you think? Are we buying power? Are we buying power? Let's think about that. Let's say you live in a little apartment and you have 5 100-watt light bulbs because you like a lot of light, and you have 1 500-watt toaster, and that's all you own. It's a simple room. So how many watts would you have? You've got 5 100-watt light bulbs, you got 1 500-watt toaster, 5 100-watt light bulbs, and one should be 1,000 watts, right? 1,000 watts, right? 1,000 watts. 500 for the bulbs and 500. Do the bulbs change and do the toasters change with power, or do they have the same power every time you turn them on? We're going to leave it the same. We're not playing that game. If you want to play the loophole game, you go and become a lawyer, and then you go and fight for people's rights that have toasters that change what. But this person bought the simplest toaster they could buy. So, does the power change? No. So that means every month you'd be paying the same, like volts, right? And do you pay the same phone bill every month? Oh, that's a good question. Do you know whether you pay the same phone bill phone bill. I've just changed it to phone. Do you pay the same electricity bill every month? Anybody know? No, you don't. If you use more electricity, you pay more, right? So it can't be watts either. So what is it that we're paying for? Yep. Yeah. Yep. Oh, yeah, that's right. You saw it on the PowerPoint. You sucked me in. But somebody had just said it. Joules. We pay for energy, all right? Energy is that combined ability for something to do something. Whether that energy is in a person, you've got lots of energy, you can run up a hill a bunch of times, or if it's falling water, is way up at the top of a waterfall, it's got lots of energy as it falls. Electrically speaking, we pay for energy, all right? And that's because that energy has to come from another location, whether it be the nucleus of an atom in a nuclear power plant and Bruce Nuclear, or whether, like I said, it's falling water at Niagara Falls, or it's the wind energy blowing those turbines around. The energy is what we're paying for in the end. Yes? Solar panels could collect solar energy and push energy into the house. Okay? Yep.
And does that really actually, I know that works.
Okay, so what happens is our electrical system, you can think of the electrical system in the province of Ontario just like an electrical system in a house, all right? There's a big line that comes in from the road, all right? And that's going to push electricity into your house, all right? And in actual fact, if nothing's turned on, there's no electricity flowing into your house, okay? As soon as you plug something in and turn things on, electricity flows into the house as quickly as you're using it, all right? So the energy moves in just as quickly as you use it, all right? In actual fact, electricity can't flow in unless somebody's using that power, that electrical energy, okay? So in the province of Ontario, every house is pulling electricity in, energy. A solar panel, okay, will push energy out into what we call the grid. And the grid is all the wires you see up and down the side roads and, the big towers between Churchill Line and LaSalle. You know what I'm talking about? All those great big towers. So in a big system like Ontario, the same amount of energy that people are using is the exact amount of energy that's being pushed into the system. If people aren't using enough, they've got to shut down generators because you can't push more energy in than is being taken out. You can't inflate or store the energy in the wires. Whatever's going in has got to come out. Correct. So there's some really smart people sitting at a great big board with computers, and computers are monitoring the use and are bringing electricity in or shutting electricity down depending on use. Yep. So if you have a solar panel, if you're using it in your house, you're using it. If you're not using it all, it's got to go somewhere. The excess can be pushed into the grid as long as someone's there to use it. Okay? If no one's there to use it, the solar panel, it would experience a back voltage and it wouldn't be able to push it in. It gets pretty complicated at that point. So we use energy. Yes?
Okay, so you're saying basically turn off the light?
Yeah.
Is there no electricity used?
Correct.
But, okay, so how come, like, if our family goes away, how come they, like, turn off the lights, they also turn off, like, they, like, do something with, like, they turn off certain things, so it's not using it, but it's off.
Yeah.
Okay, they'll turn off, I don't want to say the wrong thing.
They'll turn off power bars, or they'll unplug TVs. No?
They'll turn off, like, they'll go to, like, the, like, their normal,
They'll turn off a master breaker and shut everything down.
how to get to that.
Well, they really don't have to. They really don't have to. It could be maybe just a safety conscious thing to make sure that the whole system isn't electrified. Things like TVs and computers and cable boxes, they always use a little bit of electricity even when they're not on. And that's because there's a little computer in there keeping everything in mind for when you do turn it on. And some people like to conserve enough electricity to say, we don't want to waste that electricity, we're shutting everything down. It could be that they don't want the background electricity that's being used by some of these devices to draw some electricity at time. But you're right, if you had everything unplugged, you went around your house, unplugged everything, that would be the same as that switch being switched.
So if you went away from,
Yep. Well, you see, electricity bills work a little different. You don't only pay for the electricity. You also pay a charge for the maintenance of the wires. All right, it's called the delivery charge. So there's always a charge on top of that you then pay to the company that has to go around and make sure all the wires are together. You know what I mean? They're the Hydro One guys you see driving around fixing wires and that type of stuff. They have to be paid. So you also pay the delivery fee. So just by being there and connected to this grid, even if you didn't use any electricity, you have to pay for that upkeep of the system. So you'd have to still pay that charge. There may not be an electricity use charge, but there'd still be another charge to it. You shouldn't be able to do that because the voltage that's coming in sometimes is higher than 120. It can be like a 240 voltage depending on what type of service you have. But that device that's pushing the current into your house has the capability of moving a lot of current because it has to take care of all the things you plug in, right? You might plug in something that's maybe only 90 watts or 100 watts, but you total all those watts up. Remember, we did that yesterday, and you're getting a big current. You fiddle with the wires that are coming into your house, and you can get burnt. Don't get it burnt? No? See what I'm saying? Rubber gloves? No, too strong. You can't do it. Okay, so let's talk about how we pay for this stuff and how we can calculate how much we're paying. That's what we want to talk about today. So you can see here, if you were already writing, don't worry about that. Electrical energy, not power, is sold by the electrical companies. Yeah, we're going to use it again because we know the power of our devices. We want to figure out how much energy we're using when we run it. Okay, so we already have this equation. But remember, we don't pay for power, we pay for energy. So I need the energy version of this equation. Just write it down. So what's the energy version of this equation? Jessica? P times T. Power times time. Now I'm writing it like that a little different than the way we've been doing it. We've been just putting P beside T. That's great. That's because I'm going to add another step to this. Now, we've already talked about the units. What's the units for energy? What's the units for energy? Tristan? Nope, that's not the units for energy. That's the units for power. What's the unit for energy? Joules. Joules. Now, a joule is really tiny. We did a calculation yesterday to determine how much energy was used when a machine was running for, I don't know how many hours was it. Do you have your notes? Can you flip back to that question? It had a big number of joules. I remember whoever told me the answer didn't know how to say the number because it was so big. It might have been Danton. It just, yeah, it's not that it matters. Who was it? It was Jay? It doesn't matter. It doesn't matter who it was. What was the number of that? What was it, Jess?
It was, 16 million, no,
One,
it's got 4 zeros.
yeah, 1,620,000 maybe? 1,620,000. And what was the machine that was running? What was the machine in the question that was running?
200-volt outlet,
Yeah?
and a home, yeah, and 100, or 1.5 amps of current.
Okay. And just for amount of time. And it doesn't say what device it is, right? It's just a particular device. Oh, it was a television. It was a television that was being used for 2.5 hours, and it used 1.6 million joules of energy. How many joules do you think you would use for your entire house for a month if running a TV for 2.5 hours used 1.6 million joules? A lot. So, billions and billions and billions and billions. Maybe not quite that many, but a lot. Now, that means a joule is too small. If we were to pay for joules, then the cost would be a difficult thing to calculate because a joule is so tiny. So we need a new unit for power. All right. The unit that we use is something called kilowatt hours. Kilowatt hours. You may have heard of that before. So, if we're doing a cost of electricity problem, our power is now going to be in kilowatts, a large number of watts, thousands of watts, and our time is going to be in hours. And when you multiply a kilowatt with an hour, we could give it a new name, but we're not. We're literally going to put the two units together, and we're going to call the energy unit a kilowatt hour. All right? And that's what you pay for when you pay for electricity. Kilowatt hours. So we have to change our units in order to do electricity cost calculations. Yes?
You don't have to do does the E still go in front of it?
The equation is the same. It's just our units are different. Now instead of watts, we're going to have kilowatts.
Will the time be in hours?
Time will be in hours, and then we'll get our kilowatt hours. Okay. So, in order to do these calculations, we have to do some conversions. We have to convert from watts to kilowatts. Yep, we can get calculators out. So to do our conversions, we are going to, to do our calculations, we need to do a conversion. So let's do some practice conversions here. Please write those down. Now I've moved our metric conversion chart over to the other side here so we can take a look at it. We're going to need it in the next unit. We'll need it today as well. Remember, kilo has a power of 10, which is 10 to the power of 3, right? Remember, that's equal to 1 with 3 zeros. That's what the power of 3 means when we have 10 to the power of 3. And that means that there are 1,000 watts in a kilowatt. Okay? So a kilowatt is a big thing, just like a kilometer is a big thing. There's 1,000 meters in a kilometer, or a kilometer, if you wanted to say it that way. All right? Which means if I have 200 watts, I've got to move my decimal place 3 steps, but I got to make sure I pick it the right way. What is 200 watts going to be as kilowatts? Which way am I moving it, Danton? Well, tell me the value. Tell me the number. It's 0.2 kilowatts. Excellent. I am moving that decimal to the left 3 times because it's like dividing by 1,000. I got to divide by 1,000. Okay? It's just like going from milliamps to amps. Because I'm going to a bigger unit, I got to make that number smaller. So what would 375 watts be as kilowatts? Joel? 0.375 kilowatts. Are we getting the idea? After 2? 2,500 watts? Yep. 2.5 kilowatts. 2.5 kilowatts. So that's a pretty easy conversion. Boom, boom, boom. Move it over 3 times. Time's a little tricky because time is based on the number 60. It's kind of a pain. Instead of it's based on 10, it's based on 60. So some of them are easy. 30 minutes, how many hours is that? Yep. It's a half an hour. You know, we know some of them that are obvious, right? 30 minutes is a half an hour. If you wanted to show me the calculation, 30 divided by 60, 0.5, but we know 30 minutes is a half an hour. So that's an easy one. 0.5 hours. 45 minutes could also be an easy one, even without calculating it. What do you think? Jade, what do you think? 0.75, right? Because it's 3/4 of an hour, right? Or you could do 45 divided by 60. 0.75 hours. If I get something like 25 minutes, then I might do a 25 minutes divided by 60 minutes. I might write it down that way, do a calculation. What's it going to be? Yeah, Jewel, what do you got? Sorry? Shouldn't be 41.7. Nope. 0.417? 0.417 of an hour. Okay? 0.417 of an hour. Okay. Now that we know how to convert, we're able to take the number of watts and the time in minutes and take a device that's running like, say, 5 100-watt light bulbs. If it's running for, 35 minutes, right, 3 times a week, how, many kilowatt hours would we use? So we now can start putting together our information. So let's do some examples here. Oh, okay. Oh, there's one more equation that we need. Sorry, and it's got it. There it is right there. Write the equation down at the top. Sorry about the animations. I worked on this PowerPoint last week and I didn't fix it. So to get the cost, all right, to get the cost of something, we're going to take the power times the time, which we just learned about on the last slide. The power in kilowatts times the time in hours. And now we're going to multiply that by what we call the rate, the amount in which the company is selling the electricity to us for. In the problem that I've got written out here, I've just chosen 12.5 cents per kilowatt hour. And that's actually not too far off the actual cost. I did a quick little search. I did a little Google search here. And these are the Ontario rates. All right, that's okay. We'll get back to it. The province of Ontario has different rates. Peak time, which is more expensive when people are using more electricity, and then off-peak time, all right? How many of you have an electricity meter that shows digital numbers on it? It's got numbers on it. It doesn't have dials on it. There's 2 types. The old type has dials on it, like a bunch of clocks. The new type has just a digital number on it. How many people know where their electricity meter is? Go ask your parents where the electricity meter is and have a look at it this evening, okay, or this afternoon. You'll find that it either has a digital number or it's got dials. Yep. It will be outside the house. And it'll be a round thing like this with a plastic dome on it. And it's got a gray wire, gray thing going in and a gray thing going out, right? And that's coming in from the outside service, and then that's going into your house. And that machine, it runs as the electricity flows, and it counts how many kilowatt hours you're using. Yep. It's built very strongly, and it's outside the house, so the electricity company can come and take a look at what the number is.
They draw with like spray paint, put stuff in their yard, right? Something else.
That could be anybody doing maintenance, but if you have an underground cable, let's say somebody wanted to dig, they may come and locate that cable, but that's not to check your electricity stuff. No, that's not a thing. Anyway, everybody hold. If you have one of these fancy digital ones, you can see, here we are November to April, from 8 a.m. to 11 a.m., you'd be paying 13.4 cents per kilowatt hour. That's the higher value. If you're on the mid in the afternoon, this is in the winter, 9.4 cents per kilowatt hour. If you want to run your electronic devices and maybe do laundry or run a big electric dryer, if you do it overnight, 6.5 cents per kilowatt hour. So you can see it changes quite greatly. So I just simply picked a number that was close to the middle. All right, let's do the calculation now. Before I can do the P times T times the rate, I need to write the power in kilowatts. How many kilowatts is 60? How many kilowatts is 60? Yep, Jack? No, it's not. That would be only 2 movements. I got to move one more. 0.06 kilowatts. What's the time in hours? Yep. 0.5. 30 divided by 60. Now I have the kilowatts, the hours, and the rate, and I can multiply them all together. The energy is equal to 0.06 kilowatts times 0.5 hours times 12.5 cents per kilowatt hour. I'm not going to put that in the equation. I'm just going to leave it right there. How many cents did it take to run that? Rachel, what do you got? 0.375 cents. Now you might think that's not a lot. And you're right, it isn't. It's not even a whole penny. Okay? But that's just a small device like a 60-watt light bulb running for a half an hour. Okay? That's not a lot. Okay? All right. Here's a second way in which we can have our questions. What do you mean? I don't understand the question. No, it's not. It's a different question, but it's also written a different way. Look at what I'm given. I'm given the V, and I'm given the I, and I'm given the time. What do I have to do first before I can solve this problem? Yep. What equation am I going to use for that? It's IV. Yeah, or V times I is the same. I just have it memorized as IV. P equals IV, or V times I. It's a material. So you'll notice we can have it in 2 ways, all right? All electrical devices should have information on them pertaining to either their power or the amount of current they draw and the voltage. If you look closely at I was looking at a power supply for a Chromebook. On that power supply, you can see that information. At the back of your televisions or refrigerators or microwave ovens, there's always a panel at the back that will either tell you the power or it'll tell you the voltage and the current in which it draws. From that information, you can determine how much it would cost to run. 1.3 amps times 120 volts. What's the power of this machine? Yeah, what do you got? 156, and what's this unit? Yeah, you're right, it's watts. From this equation, we get watts. But we have to convert that. So I'm going to put another equal right beside it. What will it be in kilowatts? 0.156 kilowatts. All right, so we're in kilowatts. We're in good shape. Look at times given in hours. No need to make a switch on that. I can now do power, time, and rate. I don't want to wait. We're in the same question. We're A and B, so we're going to assume the rate's the same. We're going to assume the rate's still 12.5. So cost, not Ross, cost is power 0.156 kilowatts times 1.5 hours times 12.5 cents. And how much did it cost to run this machine? And I'm getting the same people. That's okay. Jewel, what do you got? 2.925 cents. We've probably got extra digits here because we really only know the time to 2 digits. So 2.9 would be fine, but that's okay. Yep. I use the I here to get my watts. No, I don't, because it's been combined into the power. Okay? Now, remember at the very beginning where someone said, do we pay for current? And I said, yeah, kinda. And then somebody said, do we pay for volts? And I said, ooh, not really. And then somebody actually said on this side of the room, is it a combination of current and volts? It is indeed, because that combination of current and volts is our power, okay? Which then we put the time on the end. One last example, and then I'll let you work. Actually, before I let you work, I'm going to do a little review of all of our equations, and then I'll let you work, okay? Do you have a question, Rachel?
I just didn't like it's probably a non answer, but is hydro and electricity the same thing?
Yeah, no, this is a good question. This is a good question. You can write that question down as I'm discussing it. The question is hydro and electricity the same thing? Hydro is a prefix. I don't know whether it's Greek or it's Latin. It literally means water, all right? Hydro means water. The element hydrogen literally means water forming. I'll explain to you why it has that name when we do chemistry. The reason we call electricity hydro in the province of Ontario is because the first power generation, actually the first electrical generator ever in the world, was built in Niagara Falls, and because it used falling water, we call it hydroelectric power, because it was from falling water that moved the generator, all right? From that, the company that was formed was called Ontario Hydro, because all of the electricity came from falling water. So in Ontario, we still have this old idea of calling electricity hydro, even though that really means water, okay? So electricity or electrical power is what the rest of the world calls electricity. Here in Ontario, we call it hydro. And so if you go anywhere else in the world, you know, and you're visiting people, ask them, hey, do you ever have the hydro go out? And they'll go, what are you talking about? They have no idea what that means. It's only in Ontario that we talk, Quebec as well, Quebec Hydro as well, okay? It's very local in this area. Yeah, it's very local. Yeah, okay. 100-watt light has been left on for 13 hours per day. If the cost of electricity is 18.3 cents kilowatt hour, determine the cost for keeping this light on for a year. That's correct. So we've got to attack this question in a couple of ways. There's two ways in which we could do it. How could we do this? Somebody give me just a plan. Okay, Jack, what do you think?
Do it normally and then multiply 3.
Find the cost for a day and multiply by 365 days. Perfect. Yep. To get the total hours and then get the cost. Both will produce the same answer. I don't really care which one. Now I'm got to pick favorites here. Jack, you're my favorite. Oh, you knew I was going to go that way, didn't you? That's fun. Okay, power is 100 watts, which is 0.100 kilowatts. The time is 13 hours per day. That's already in hours. So cost per day is going to be power, 0.100 kilowatts, time, 13 hours, the rate, 18.3 cents, equals, Rachel, what do you got? 23.79 cents per day. Don't clear your calculators, all right? The biggest mistake by many students is they want to clear that calculator away before they move on to the next calculation. Don't do that, because what am I going to do with that number? Times it by 365. So 365, doesn't matter the order, times 23.79 cents per day. And, yeah, what do you got, Grace? 8,683.35. And what's the unit on this? Yeah, this is cents, right? Or, let's turn this into something that's more functional than cents. What would it be?
Is it 800?
No, it's not 800.
800.
Well, there's 100 cents in a dollar. So how many dollars are we dealing?
$8.68.
No. Jack, what do you got? $86.83. $86.83.
I do that the whole time.
Of course you did. Oh, I thought I didn't press the start button on my record, but I did. Woohoo! That's exciting. All right. Okay, there's a worksheet, and there is a question out of the textbook. Even though we haven't been using the textbook much, there is a question in there. I would worry more about the worksheet. The worksheet just has a bunch of questions on it. I'm going to stop recording this right